All right, so for the start of this tutorial, I'm going to invite you to open up the chapter 1, the introduction to graphs. Inside here, there's some preliminary knowledge that's pretty important. I want to make sure you walk away with a real solid set of fundamentals that will help you when you start attempting the exercises. So let's talk about graphs. Graphs are extremely useful as a data modeling tool. The key thing that we use graphs to as a representation for is complex relational problems. Okay, so I'm not talking about your relationship problems between you, your romantic partner. I'm talking about relational problems between entities. All right, so let's start first with a formal definition of graphs or slash networks. So networks, probably something that you're intimately familiar with. In the slightly more academic literature, networks are more formally known as graphs. So these two terms are interchangeable. By the time you hit my level of experience, you can't stand someone referring to charts as graphs because they get like there's this term overload thing that happens. But that's for the more experienced version of you to worry about. So, what are the contents of this thing that we call graphs? Well, there are two primary things. Firstly, you have a node set, which are which semantically refer to the entities in your graph, and then you have the edge set, which record relationships, again, which we get to define between the entities in the graph. So, for example, if a node set is a mathematical set of some kind, it does imply a few things. So firstly, every node must be unique. You can't have duplicate nodes inside there. Secondly, from the edge set, no edge can exist between elements. So sorry, let me backtrack a little bit. The second set that we are concerned about is the edge set, and it's a set of tuples in which each tuple is a pair of elements. All right. So one very important property of the edge set is that if you extracted every node from the edge set E, this guy over here, and calculated what the set of nodes are that are present in E, every node inside E must be a subset of N, right? So the reason is because not every node in N might participate in edge. You might have singleton nodes. So the node set in E is always going to be a subset, or equal to the node set in N. Now, if you draw out networks or graphs, the canonical way that we sort of draw it are such that the nodes are circles. The nodes are our things, and then edges are lines between those things. All right, and we'll see in a later chapter we're actually going to explore how you can make graph visualization that much better than the hairballs that you might have been exposed to in the past. So now that we've explored what the proper definition of graphs are, let's explore what some examples of graphs might be. So first off, I'm a biologist by training. That's my background. So one graph that I'm very fond of is a protein-protein interaction network. And so here, the graph is defined as follows. You have nodes, which are the proteins, and edges, which are defined as one protein is known to bind or interact with another. Now, herein lies a really important point. The definition of the edge really matters. So between proteins, interactions can have like multiple different types. I can have a binding interaction. I can also have a protein not only bind but also cut another protein in two. I can have a protein that takes another protein and glues it to a third protein. So now we have like a three-way interaction we have to model, right? So but the key point here is that the definition of the edge really matters because that changes what you draw lines between. And what you draw lines between gives rise to the most important, like interesting piece of a graph. All right, so another example that we might be more commonly familiar with is an air transportation network. And so what do you think would be the graph's nodes and edges? Well, one way we could define it is the nodes are the airports and the relationships or the edges are there's at least one flight carrier that flies between those two airports. And maybe one that we're now, Homo modernus, modern human beings are very in tune with is the social network, right? So we've got a social network like Twitter. Individual users are the nodes. Relationships are one user has decided to follow another. So now, at the end of this chapter, I'd like you to maybe do a little exercise for yourself. What examples of networks have you seen before in your particular profession? So write them out. And the most important thing I'd like you to really think about is what is a node and what is the specific definition of an edge? And can the definition of the edge, is the definition of the edge that you have muddied enough and not precise enough that you need to refine it further? That's the most important thing that you have to define. Okay, so with that, I'm going to move on to the types of graphs that you might encounter. Basically, there's two key types that I want you to keep in mind. Firstly, there's the directed graph, and then secondly, there's the undirected graph. And to illustrate this, I'm going to illustrate the difference. I'm going to show you two social networks. So Twitter is an example of what we might call a directed graph. And why is this so? The key lies in how we define what an edge is, right? Okay, so if we were to talk about the Twitter follow graph, one user can follow another, but the other might not necessarily follow back. And so as such, there is a directionality to the relationship. On the other hand, LinkedIn is what we might canonically call or intuitively call an undirected graph. And why is that the case? Well, if we were to talk about the LinkedIn connection graph, anytime two users are connected, we automatically assign a bidirectional edge between them, and therefore, for convenience, we collapse the bidirectional edge into an undirected edge, therefore giving us an undirected graph. Now, strictly speaking, you actually can take the LinkedIn graph, and if you had additional information, you could make it into a directed graph. And here's how we could do it. Two people are connected, yes, but one of them initiated the connection and the other accepted it. And in that way, we see sort of like an imbalance or inherent directionality between the edges. And so that way, we would have the relationship become a directed edge. So the final thing that I want to point out in this little section is that really it's the edges that are interesting. It's not the nodes, right? Everything that's interesting about a graph arises from its structure, and the structure is defined by which edges are connected with which other edges. So if I were to think back in grad school, I think this was in 2015, there was an instructor, John Quackenbush, a guest lecturer, Professor John Quackenbush at the Harvard School of Public Health, and he had this really cool quote from his seminar. Now, I remember the quote and not the seminar, unfortunately. I can't tell you what it was, but really, the heart of a graph lies in its edges, not in its nodes. And this is really important to remember because, once again, everything that is interesting about a graph arises from its structure. That is to say, how you can pass messages most efficiently from one user to another in a social network, or how you might figure out the shortest way to transport things from one place to another. All of that is given by the edges and not the nodes. So it's really important to remember. All right, so with that, we're going to end chapter 1. There's a little exercise that I gave you above, which is to think about what kind of networks you have seen in your profession. I'd like you to, again, think about it. And once again, think about how precise you need to make the definition of an edge such that you can meaningfully model something in your day-to-day work. Once you're done with that, feel free to move on to the next chapter, chapter 2, which is an introduction to the NetworkX API.